I'm very pleased to have with me today Richard Dawid, author of String Theory and the Scientific Method, and we're going to be talking today about the ideas that he proposed in that book. So welcome, Richard.
Thank you.
Okay, so in your book you propose a novel account of scientific confirmation that is special for string theory, as you were kind of starting to hint at there. Maybe it'd be useful to just first, your account is, I think, so non-empirical confirmation. What's the more traditional, I think, empiricist account that you're modifying and building on, while giving an alternative to?
Yeah, the traditional understanding of theory confirmation in physics and in the philosophy of science is based on the idea that theories can be confirmed by empirical data that can be predicted by the theory. So the mechanism is the theory, you develop a theory based on some observations, and that theory makes predictions. And now you test the theory by checking whether those predictions are accurate or not. If they are, that amounts to confirmation. If they are not, that amounts to a refutation of the theory. So that's the canonical understanding of theory confirmation. And one might add that in particular in the context of philosophy of science, theory confirmation doesn't mean that the theory is considered conclusively proven in any sense. It only means that the theory becomes more probable based on the empirical evidence. So it's a gradual improvement of the prospects of the theory for being true or viable that is characterized by this concept of theory confirmation.
Could you just briefly tell us a little bit about why it's so hard to empirically test string theory?
There are two main reasons why this is so hard. One experimental reason and one theoretical reason. The experimental reason is that it is highly plausible to assume that the characteristic length scale of those strings, which are posited in string theory, is extremely small. So it is so small that it cannot, the length of the string cannot be discovered by traditional means. So in physics, there is the general rule, because of quantum mechanics, that you need higher energies in order to test smaller distance scales. So the smaller the distance scale you want to test is, the higher up you have to go with your energies. If you want to go down to those distance scales that presumably are the characteristic distance scales of string theory, you end up being so high up with your collision energies that you will never reach them based on collider technology. That's the experimental reason. The theoretical reason is that it's extremely difficult to understand string theory to a sufficient degree to extract predictions from the theory. So we have a lot of concepts or a lot of conceptual understanding about basic characteristics of string theory, but there is no full understanding that would allow concise, quantitative predictions that are made by string theory at this point.
When you say string theory, doesn't make predictions that are amenable to empirical testing, do you mean nobody knows its consequences for anything empirical at all, or are you talking more about very specific predictions, and I suppose in particular ones where you would see a difference from the predictions of contemporary physics? The string theory makes no quantitative predictions. So you don't get predictions with respect to the parameter value of anything you observe in the world. However, it does have implications, or it enforces specific general claims about the world. For example, it implies that there is gravity in the world. It implies that the low energy limit of string theory is a gauge field theory. Things like that. So very general implications can be extracted from string physics already at this point. But of course, if you want to
to have a strong empirical test of a theory, you want to get some numbers. You want to say the string theory predicts 95 point something, for example, and now we test it and we find that's the number we find.
Okay, so here's the big question. What's your alternative account?
So maybe I should say a few words about the reasons why I want to have an alternative account. And the reason is that if we look at string theory in particular, scientists, string theorists, have a considerable degree of trust in that theory. And they trust that theory even though there is no empirical confirmation for that theory. So my idea is to generalize the concept of confirmation in a way that can account for that, for string theorists' trust in their theory. So the strategy is, or the idea is that observations can amount to confirmation of a theory, even though those observations are not of the kind that are predicted by the theory. So to give one example, scientists may observe that there are no alternatives to a given theory that have been found, even though they have looked for such alternatives. That's clearly nothing that is predicted by the theory. So the theory doesn't predict that no one will find an alternative theory. But still it is an important observation with respect to the question whether or not we should trust the theory. If we don't find an alternative for a very long time, that can be a good reason for trusting that theory.
So that's an observation of, a sort of historical observation of the scientific process rather than of space and time and quantum processes.
Exactly.
I see.
Exactly. And a different line of reasoning that also amounts to non-empirical confirmation would be that in the specific research field, theories that have been trusted before tended to turn out empirically successful once they could be tested empirically. So that also gives a reason for trusting the theory in question.
And again, we can observe that from the historical record and seeing the past successes, and so
exactly.
And yet, it's not a prediction of the
it's
theory
not a
itself.
prediction of the theory.
I understand.
Yeah. And so there is a third strategy that also play an important role, in particular in string theory, and that's the observation that the theory has been developed for one reason, in order to solve a specific scientific problem. And later it turns out that actually the theory can be applied to all sorts of different problems. It wasn't made for, so to say. And it is successful in providing explanations in those other contexts. And if that happens, that also tends to be a basis for trust in a theory. And if you ask string theorists in particular, often they would say that actually that's the main reason for their confidence in string physics.
Let's talk a little bit about some of the objections that people have raised, and I think George Ellis and Joe Silk in an essay in Science about a year ago made I'm not sure an objection you've heard a number of times, that you're proposing science doesn't need to be falsifiable. So what do you say in response to that kind of claim?
This kind of criticism is based on a misunderstanding of non-empirical confirmation. Because non-empirical confirmation is based on the understanding that the theory is empirically testable in principle. So specifically, non-empirical confirmation is understood as a method of understanding whether or not the predictions of the theory, once they can be tested, will be tested successfully. Now, if there are no predictions of the theory whatsoever, that simply doesn't apply. So no empirical confirmation doesn't work either. To be sure, non-empirical confirmation can also be applied in contexts where we don't know yet what the specific predictions of the theory are. And this is the case in string physics. So no one can calculate quantitative predictions of the theory. But in order to use non-empirical confirmation, one needs to assume that there are some predictions, whatever they may be, once the theory is fully developed.
So it's more a matter of of our current ability to actually falsify the theory than its in principle falsifiability. String theory has gone through various cycles of excitement, which are usually based on some success in solving some problem that physicists perceived, some advance, some theoretical advance, some conceptual advance. How do those kinds of successes that aren't empirical predictions, but how do those kinds of successes play into the picture that you've described? Do they give another kind of confirmation, or do they play a role in non-empirical confirmation?
So the successes of string theory at a conceptual and theoretical level are, one may say, of two kinds. First, there are successes with respect to developing a consistent theory. So, for example, people try to understand how to formulate a string theory that is that can also describe fermionic particles, and for a long period of time that people don't know how to do that. And at some stage, they understood how to do that, and that was a big breakthrough, and that generated the first big excitement about string theory. So these kinds of successes imply or suggest that there is a consistent string theory at all. Of course, if there is no consistent string theory, we shouldn't trust the theory.
There is no theory.
There is no theory. So of course that plays an important role as a foundation for those considerations of non-empirical confirmation. The second kind of success are successes that can be characterized in terms of the third argument of non-empirical confirmation I mentioned, in terms of the unexpected explanatory interconnection argument. So one success of that kind would be, for example, that it turned out that string theory can provide a microphysical explanation of black hole entropy, without going into the details what that means. But this was an open question, how to do that, and string theory at some stage was understood to be capable of doing it in some specific cases at any rate. Now those kinds of successes play a crucial role for one of the arguments of non-empirical confirmation, namely for the arguments of unexpected explanatory interconnections. So these successes play a role, but they don't amount to non-empirical confirmation on their own, because non-empirical confirmation is based on or aims at understanding whether or not it's plausible to assume that there are no alternatives to that particular theory. And in order to understand that, we need more than just observing that the theory can solve some problems.
So we'd like to know many other possibilities can't solve those problems, for instance, or
exactly.
that kind of problem that would rule out possibilities,
yeah,
rather than just be a success for string theory.
Right, exactly. If it happened that string theory, to stick with the black hole question, that string theory can provide that explanation, but there are lots of other theories that can do that as well, that would not generate an awful lot of trust in string theory, because all of those other theories might be viable as well.
Suppose string theory does receive non-empirical confirmation, as string theorists think. What exact attitude should somebody who accepts that confirmation have? So just to give some possibilities here, I mean, should they be believing string theory is true, think it's the most likely account we have here, just one plausible account, something that's worth investing time in, something that's uniquely worth investing time in, the best bet for investing time in it? What attitude should people take to string theory if they accept the non-empirical confirmation?
So clearly the concept of non-empirical confirmation is meant to be more powerful than just being a tool for assessing whether or not it makes sense to work on the theory, or to assessing whether or not we can justify working on that theory. So it is it should be understood as a method of understanding something about the question whether or not the theory is actually valid, a valid description of nature. And it is to be understood in probabilistic terms, so it increases the probability, the probability we attribute to the statement that the theory works as a viable characterization of nature. So what that definitely means is that we can be confident, based on strong non-empirical confirmation, that the predictions generated by the theory are going to be confirmed by experiment. Whether or not that amounts to declaring the theory true, of course, is another matter. Truth is a very difficult concept, and it's a very general question in the philosophy of science whether one should use the concept of truth at all when one tries to characterize the status of theories. So one probably doesn't want to insist on the concept of truth.
Okay, so I think but the piece that you are willing to assert is, might put it like this: what the non-empirical confirmation does is make you confident, more confident, really quite confident, that when the empirical confirmation, or when the empirical tests are made, the theory will be empirically confirmed as well.
Exactly.
Okay.
Yeah.
Okay. So part of the non-empirical methodology, as you've said, relies on there being no alternatives, this being the only alternative theory that people know about. But what about alternative theories of quantum gravity that maybe viewers, of our channel have been seeing about? Say, loop quantum gravity is the most prominent example. Aren't there alternatives, and how does that fit into the general picture?
So with respect to loop quantum gravity in particular, one has to distinguish between the question whether there are alternatives research strategies with respect to the issue that is addressed by string theory, and whether or not there are alternative theory at a specific level. If we look at the question, is there an alternative theory to string theory as a consistent overall, a satisfactory, consistent description of all fundamental interactions? At this point, I would say, and string theorists would say, that there is none. Loop quantum gravity is not an alternative theory at that basis, an alternative theory that addresses this question, because it only focuses on finding a quantized theory of gravity. So it's not a theory that covers all interactions. Gauge field theory plus gravitation, it's only a theory that quantizes gravity. This, of course, doesn't mean that loop quantum gravity cannot in principle develop into a fundamental theory of all interactions. If so, it would amount to an alternative to string theory. But at this point, it doesn't.
Are any other sciences confirmed by this non-empirical method? I think in your book you talked about paleontology, for instance. Could you just talk a bit about your views in those regards?
Mm-hmm. Yeah, I think that non-empirical confirmation plays an important role actually in many scientific fields. It's not something that is specific to physics or specific just to string physics, let's say. There are certain preconditions for that in a field that make non-empirical confirmation important. First, you need to be in a context where it's difficult to acquire empirical data, and second, there have to be considerable conceptual constraints on theory building. So you need to have reasons to trust a given theory just because it's difficult to find anything else that can account for the data you have. And paleontology, or for that matter, all kinds of historical sciences, are nice examples of that. If you think about the situation in paleontology, you try to develop theories, for example, to reconstruct extinct species, and you
have to reconstruct them based on the evidence you find in the ground. And that may not be a full cask of a full skeleton of an animal. It may just be very scarce evidence, some bones, whatever you find, and you don't know whether you're going to find much more than what you have. So if someone comes up with a hypothesis, it is important. First, of course, it is important that this is coherent, the hypothesis is coherent with the observations that have been made. But second, it is also important to emphasize that this is a meaningful scientific hypothesis, that this is not radically underdetermined by the evidence that's available. So the scientist needs to argue based on strategies of non-empirical confirmation that it's not plausible to assume that alternative explanations of the evidence that has been found can be developed. And only if let's say a reasonable case to that end has been made, the hypothesis is taken seriously by other scientists in the field.
Richard, thank you very much for talking with us and answering my questions, and I'm sure our viewers will find what you said very enlightening. Thank you very much.
Thank you.